Okay. Hello, everybody. Can everyone hear me okay? Yes. Good stuff. Right. So just in case anyone's wandered into the wrong room by mistake, what I'm going to talk about today is cybersecurity, and I'm going to give you essentially an introduction to some of the stuff that we're doing around the cybersecurity space and some of the solutions that we have to solve problems in cybersecurity today. Also going to go over some of those problems. The other thing I'd like to just give a little plug for is that we have some much deeper tech sessions coming up over the course of the rest of the conference. Tomorrow, next door at I think this time, one of our core developers will be giving you a much deeper dive on some of the core code that goes into this and some of the deep parts of the analytics. We've then got another session on Thursday, which is about the model as a service component, which I'll discuss briefly today, which talks more about some of the machine learning elements and how to actually implement some of this stuff. But today, I'm going to give you a little bit of an overview of how we use big data platforms to solve cybersecurity problems at scale. So, to introduce who I am and why I'm here, I am a product manager for cybersecurity at Hortonworks. I've been with Hortonworks for quite a while, really focusing on data science and big data, running Hadoop, using Hadoop to solve problems, and found that I was solving this cybersecurity problem quite a lot. I also just wanted to introduce our lovely little elephant here. This is a lovely little elephant that lives in the London office. And often, actually assembling solutions on Hadoop can be a little bit like origami. You start with some fairly straightforward, simple pieces, but actually knowing how to fold them, where to put the creases, and how to build them into the kind of complex solutions that you require to actually meet a problem can require a little bit of skill. So I think he's quite a nice little metaphor for what we're doing here. So when we look at cybersecurity, I want to think a little bit about what's coming at us. You know, where do these problems come from? What is it that we're trying to address? Where are the new threats coming from? Because it's changed a lot over the last few years. One of the big threats is, who remembers the Mirai botnet attack? Anyone get hit by that? Okay, you're all lucky, or you don't work on the East Coast for Dyn DNS. This was an attack where a botnet managed to take out a very large proportion of the East Coast of the US's internet sites by basically bringing down a major DNS provider through denial of service attack. This was all run on things like this. These are the kind of devices that are threats now. They all have CPUs in. You know, your charging cable has more intelligence than it probably needs in these days. You know, all of these kind of sources, or all of these intelligent devices are now a source of threat. I should point out that this one wasn't involved in it. This is actually attached to the side of my house and is behind the most obsessive security guy, insane firewall you could possibly manage to find, which is why none of the functionality works for me. That's the other trade-off that we have to make in security. We have to keep our devices functional. We can't just take this approach of, okay, let's lock everything down. So what happened with this attack? At times, this botnet was reported to, and reports vary, but the reported maximum attack speed of the denial of service that came from all of these devices was about 1.2 terabits per second. How many of you can handle an excess, unnecessary traffic load at 1.2 terabits? Nope, no one from Google here? This is very difficult to defend against. It's also very difficult to process an attack and even detect. It will overload most modern systems. There were about 500,000 devices involved in this particular botnet at its peak. All of these were these little hardware devices. They're generally developed by hardware guys. They're not necessarily the world's top security programmers. Apologies if there's anyone who's an embedded developer here, but generally speaking, they seem to focus on doing the minimum possible and using tiny amounts of memory and functionality. Security is often a secondary concern here. Most of the devices compromised were still set on their default passwords. They were just the kind of nothing devices that people don't think of. It's not like they're an important server, but they're still a valuable asset and they can still cause damage. So that's one of the threats. And yeah, as I say, the DDoS attack was against the Dyn DNS service originally. There's another threat. Insiders, your own people. They can be an accidental threat or they can be a deliberate threat. The other piece, the reason I use this image is you see there the mobile phone. We mentioned that you can't just necessarily take that attitude of let's just cut everything off. That used to be the standard policy of a security department. So if you've, I'm sure there are people in this room who've bought up Hadoop clusters and then gone to their security department and said, we want to bring up this cluster and put all this data on. And does anyone want to hazard a guess as to the most common first response I've ever heard from a security department there? Yeah, they say no. And then they say, okay, what is it you want it to do? We can't take that approach anymore. Things like bring your own device, things like the proliferation of mobile, things like home working, things like the kind of what used to be called the road warrior back in the day. If I'm showing my age a bit here, maybe. These are the new threat surfaces that we have to cover. So again, they're outside of your firewall. You can't just put up a bunch of proxies and a bunch of VPNs and a firewall and think you're safe anymore. The other thing is the malicious insider in that. Insiders tend to have a lot of access. If someone's been working, I don't know about you, but if you've been working in an organization for a few years, you've maybe moved around that organization for a while, you tend to get what's called permission creep. You will end up having access to a lot more stuff than you strictly speaking need. Now, you can either try and manage that in a preventative fashion, which is actually very difficult, and very few people manage to succeed at doing that, or you can take a more intelligent approach based on behavior, which is what we're going to start to talk about. The other key threats that we're seeing emerging a lot more are things like ransomware and spear phishing. So I wanted to talk a little bit about an attack which actually started somewhat after I prepared these slides, so apologies I don't have any slides on this attack, but you may have heard recently of a little bug called WannaCry, or a little worm called WannaCry. This was a classic example of ransomware which infected an organization through spear phishing, then spread through lateral movement on a convenient exploit that the NSA wrote on behalf of the hacking community and then accidentally lost, which exploited, spread around networks through bugs in old unpatched versions of Windows. These are increasingly common. This is the kind of thing that's happening all the time. They're very difficult to detect with traditional antivirus tools, for example, because the original variant of WannaCry came out. It was actually pretty brittle, and someone, in fact, defeated the whole thing almost by accident when they registered a domain name which turned out to be a kill switch for it. So that kind of got lucky. But what happened after that? In the hours after that happened, dozens of variants of the same worm appeared. Because these things are shared extensively within the community. So I mentioned that the original source of this worm was actually an NSA exploit kit which was stolen by hackers and then sold on the dark web. The variants of that are then very easily to produce. There's a market in these kind of things. People can go and buy these exploits for tiny fractions of dollars. People can buy your credentials for tiny fractions of dollars. This makes these kind of things very, very dangerous. It shows that the opposition team are collaborating heavily on these kind of things. It also shows that traditional tools just aren't up to being able to stop these kind of things. You may be able to, if you take a traditional antivirus tool, that might detect the first variant of this worm through the signature of its binary, for instance. That's how your AV tools work, right? Most of them. That just doesn't hold water anymore, because all I got to do is change a couple of bits in that code, which may or may not do anything material to it, or just a tiny little addition to that worm, and I got a whole new variant, which is spreading again. So, who are the people who are actually doing this? Who is this community of bad guys? There's an old acronym which was produced, I think, in 2014. So, 2014 is a long time ago, right? That's an old legacy approach to thinking about things. which is this concept of mises. And this was essentially an effort to try and figure out, okay, what is the motivation behind this? Why are people doing this to us? Why are these bad people spreading all these viruses? And they basically came up with this idea that a lot of it was motivated by money, flat out just let's go steal some credit cards and make some cash. Some of it is the kind of ego or entertainment kind of principle. It's just proving to your mates that you're a better hacker than anybody else. That tends to be the kind of script kiddie sort of area. You then get the kind of hacktivist people, so people like Anonymous, for example, who maybe have a political act to grind. As well as that kind of sense of belonging. This really sort of emphasizes the community element of this and status within that community. So there's a lot of sharing, there's a lot of collaboration in this kind of community. So this is our model of who we're up against, right? Well, no, not really. This is a model which came about 3 years ago to try and explain these motivations. But the motivations are actually much more complicated these days. Hacking has become a big business. It's become $1 trillion market. Selling these exploits, selling results of these exploits, selling access to organizations, selling industrial secrets, industrial espionage, political espionage, cyber warfare has become a major market. If you look at things like the Yahoo attack, for example, that was orchestrated by a small independent set of freelance hackers who were paid actively by the Russian government. They do it for the cash and they run it as a business. If you look at some of the ransomware attacks that we've seen recently, they have help centers, they have a helpline. These people are running call centers to provide technical support on how to pay them Bitcoin, to pay the ransom that their viruses used, or to pay a ransom to get your files back. So this is actually pretty big business you're up against. They've got big resources, they collaborate. They can buy, what's this? This came from a KPMG report, I think, and it costs about 5 Bitcoin. And does anyone know the price of Bitcoin today? Goes up and down a lot, but what's that? About, it's less than $100, isn't it? It's not a lot of money to buy access to 100 million compromised credentials. You also get this kind of emerging effect of essentially people providing criminality as a service. You can just go and hire a hacker. Now in that kind of environment, you're up against a very different set of motivations and a very different kind of picture to that traditional view of the kid in his basement who's downloaded an exploit kit as running a few scripts against you. That's the kind of thing you might have been able to stop with a traditional tool. But now we're talking about taking on a large organization which is significantly bigger than you are and well organized. So another lovely little stat there. If you want to DDoS one of your competitors, for example, it's going to cost you about $5. And for that, you'll get, you get to take out your competitor's network. I wouldn't recommend it, by the way. It's still pretty illegal. But this is how this marketplace is working. So in order to combat this, we need to take a very different approach as the good guys. We also have a number of challenges facing the people who are trying to defend against this. If you saw that stat that we had, it costs about $5 to mount a DDoS attack against someone. It costs the person on the defending side an average of about $40K to be able to defend against that. That kind of asymmetry just isn't going to work. You can't spend $40K every time one of the bad guys spends a $5. So what challenges are we facing? The first off is that we're just frankly drowning in data. So I talked to a lot of people who are working in traditional SOCs, and I'd say the kind of average that we're seeing from people in reasonably sizable SOCs is that each analyst sat in front of their bank of monitors is probably trying to look at about 100,000 different alerts a day in a decent size network. Now, if you're one person and you're looking at 100,000 alerts a day, we spend an average of about 30 minutes on each of those alerts. So Some of them they'll get through quite quickly, but for deep investigations, for just even being able to figure out if an alert is a real thing or not can take a significant amount of time. So you frankly just can't address that kind of volume. You're lucky if you can look at about 1% of the data that's coming at you at the moment. The other thing is there aren't very many of these people. If you're trying to hire SOC analysts, it's very difficult to, A, find the people who are trained in this. I think there was a stat of, I forget the exact number, but there are actually hundreds of thousands of unfilled job positions for cybersecurity specialists currently out there, and the projections are even higher. It's also very difficult to actually hold on to these people as well. You tend to take people, train them up, and they move on very, very fast. It's a very competitive job market. So people are moving around a lot in this, so you lose a lot of organizational knowledge. We also have a very long tail problem with this. We talk about these kind of big hacks and these large numbers, 1.2 terabits. That sticks out like a sore thumb. But a lot of the real threats are actually very well hidden. A lot of long-term attacks will last for 8, 9, 10 months, years even. The Yahoo breach went undetected for nearly 2 years. You're looking for very weak signals in a very large amount of data. So it really is the proverbial needle in a haystack that you're searching for with this. So what are we using? What's the kind of traditional solution to this right now? How do you solve this problem? Right now, we have a bunch of silos and point tools. So you've got maybe a log store somewhere, which you've got some Splunk and you've got your logs in it, and you've got probably some endpoint antivirus systems, and you've got some proxies which do application firewalling. You've got a web application firewall which has some logs, and you've probably got a SIEM solution, and you've got some threat intel platforms, and you've probably got a hunt platform of some sort, and you've got a packet store if you're looking more sophisticated, so recording all your data, and that's somewhere else over there. And then you've got a bunch of lookup tools which provide you with information about this, whatever's going on in the world, and you've got a case management system. You've got all these different data sources which are all completely separated. So, we looked at an attack recently where it was a simple phishing attack. In order to do basic analysis and triage on that attack and to establish the pattern of what was going on, the analysts we talked to looked at 7 different consoles to be able to figure out what was going on with the single alert that they received. And that is deeply, deeply inefficient. It takes a long time, and as we say, there aren't exactly many of these people, and they've already got plenty to be doing. So when you look at that kind of siloed environment, that kind of point solution-driven environment where each and every solution has to be individually integrated, you start to get something which, to big data people like us, starts to feel kind of familiar. We've been breaking down silos with Hadoop for a while now. So what else do we have? We have rules-based systems. So a lot of the, if you take a traditional SIM platform like an ArcSight, for example, a lot of these, or an intrusion detection system, a lot of these work on the basis of rules and known signatures. So take a typical rule, for example. This is a very common example. If I see 30 failed logins in a 5-minute interval, in a 5-minute window for a particular server, then I'm pretty sure that someone's trying to break in with a brute force password attack. So I'm going to write a rule which says, if you see 30 logins in this time period, then block it, right? Simple enough. So as I say, there's quite a large organization potentially attacking you, well-organized hackers, etc. They notice that being blocked, and you know what? Now they know what your rule is. So I've got all the time in the world. I'm going to try 29 failed logins and not fire your rule and not get noticed and fly under that radar. And then I'm going to wait for a few minutes and try it again. My brute force attack takes a little bit longer, but I'm not actually getting the visibility of that. Now, our approach to this would be very different. If you use a behavioral approach to this or a behavioral analytics approach to this, then you can actually customize those rules to an individual user. So for example, I don't know if you noticed, a small miracle happened when I just came up to this podium. I turned my laptop on and I typed my password correctly the first time. I think that's the first time that's ever happened. Ordinarily, I take about 3 or 4 attempts to log into my laptop, because I'm a terrible, terrible typist. Now, that means that for me, 3 or 4 failed logins to a machine is actually pretty standard, pretty normal. That's just normal behavior. However, 10 might start to look a bit suspicious because that's unusual for me. If I take someone like, like Dave here, Dave is a very precise person. And Dave, I don't think, has ever typed anything wrong in his life. He grammar corrects his IMs. So, getting a single failed login from him is actually potentially suspicious. Getting 3, like would be normal for me, is probably actually a disaster and is the start of something attacking him. So through that kind of personalization and direct user-specific behavior profiling, you can start to get to detecting attacks much faster and therefore mitigating much faster, long before they had a chance to produce any damage. So our traditional rules can actually, not only are they easy to circumvent, they also take a lot of time to actually manage. So I was talking to a customer the other day who has 35,000 different rules that they manage in their SIM. They have a team of people whose job it is to keep those rules consistent. And they can't. They've got a lot of exceptions that they've put into those rules for particular events or particular known pieces. And there's a lot of embedded organizational knowledge in that. There are rules where you kind of look at them and you go, where did that come from? The only way of finding out is you go ask Frank, I think it was Frank, or was it the other guy? And no one really knows where all these rules are coming from. They're a nightmare to actually manage at that kind of scale. So they can become a little bit of a liability just from the point of view of the amount of effort that goes into maintaining a rule set. So the other thing that we have today is we've got all these kind of shiny new tools. So there's a big trend in the market recently called user entity behavior analytics, which was the kind of beginning of this piece. There are also a lot of new machine learning-based tools and specific endpoint tools. So things like the kind of CrowdStrikes of the world, the Taniums of the world, things which provide particular point solutions and smart new algorithms. Now they are great, but they still provide a lot of point solutions. What a lot of these are doing is providing another dashboard, another tool to go and inquire about when you're trying to do triage, when you're trying to bring data together. What they're not doing is integrating that data into a single place so that you have a single view. So they're providing you with some very useful signals, but in the same way, just another set of signals to try and sift through. So how do we solve this problem? Well, of course, the first thing we use is magic, or machine learning, as most people call it. There are a lot of solutions out there right now which will say, machine learning will solve all of this. We'll just use Spark. It'll be great, and we'll build machine learning models and artificial intelligence, and it will solve all of our problems, right? Everyone heard that pitch? The truth is, it's good for solving some of the problems. It certainly is. And some of the ones where we find it particularly useful is in things like triage automation, that process of going through that long list of alerts and trying to find out if there is actually anything interesting in it. Prioritizing those kind of things, looking at the behavior of the humans in the SOC as they classify things as being real or not real. That's where a lot of the machine learning techniques can provide a lot of power to triage. The other piece where machine learning really comes in is detecting things like the unknown unknowns. So detecting the zero-day attacks, the patterns that we haven't necessarily seen yet. So this is where a lot of the machine learning techniques really pay off. However, the real challenge with a lot of the machine learning techniques is that they're kind of black box. Like a lot of those shiny new tools, they will spit out a bunch of things and say, this is a problem. But actually understanding why that is a problem, or what element of that algorithm triggered that to be tagged as a problem, can often be quite difficult. You get particularly things like some of the deep learning algorithms. You get result sets which are very difficult to explain to an end user. So when you're looking at a threat which is just kind of saying, this is bad, it's very difficult to actually address that problem or mitigate that problem. Like, sure, you found something that's bad, but where do I now go to try and fix that or to try and prevent that? I have very little insight into what's caused that. One of the things we try and do a lot in our platform and in the, particularly in the application of triage and prioritization rules is we encourage highly explainable algorithms. And also, specifically, we have a reason field in everything that we apply rules to, which is designed to very specifically target back the source of attacks. Unless you can trace back exactly where that rule came from, what triggered that rule, what made this a bad thing, then you will find it very difficult to actually then go and mitigate that problem and to figure out which IT administrator you need to go and change which system with. So that kind of explainability of machine learning is really a key thing to look for in these kind of solutions. The other thing that I would say is really important to solving these problems is real time. So the platform that we produce, Apache Metron, is very focused on real-time analytics for several reasons. Firstly, a lot of traditional platforms will essentially take all of your data, load it into a database, index it all, chug around, then you'll search on a dashboard before you actually get an answer. So you have to load all your data, ingest it, before you can even start asking questions. I would argue that when you're dealing with very fast attacks and you want to be able to get to that kind of holy grail of machine time response to that and completely automated response to threats, you don't have time to load everything into a database and then query it all out. So what we use is some of the data in motion platforms that I'm sure you have heard from extensively around this conference to be able to ask for questions of the data before it's landed. So a lot of our analytics is very much designed to work online in the stream before it's persisted to any form of data store, so that we can get much faster time to detection and therefore much faster time to resolution of problems. The other piece, or the other reason why real-time is important is correctness. In a traditional scenario, you remember the analyst I talked about who had to go and look at the 7 different dashboards to figure out what was going on. A lot of what he was looking at was the state of the world at the point at which he was looking. He's had an alert come in, and then he's gone away and he's gone, all right, okay, that's this domain name. All right, let's go look up this domain name, figure out if it's real, who owns it, do a who is query, all of these kind of things that an analyst would do to try and understand this problem. He does that, or she does that, often as not, on the point at which they're actually looking at that alert. Now, by that time, the world's probably moved on. If you're in something like a cloud environment or a complex corporate environment or an environment where things are changing a lot, then chances are that IP address that you're starting to do your investigation on doesn't even belong to that person anymore. It's moved on. It might not even belong to your company anymore if you're in a cloud-type environment. So what we do is we will essentially do all that lookup and all that research and all that enrichment work on data as it comes in. So we do it at the point of ingest, so that when we're using real-time lookups to do that, we're actually getting the state of the world at the point at which the problem actually happened, not the point at which someone got around to having a look at it and seeing where the world was then. So real-time becomes very important for the actual correctness of that data as well. And for that, we use Storm. So a number of people will ask, why Storm? A lot of this is about prioritizing the absolute real-time, low latency, getting to the answer faster, getting to the solution faster piece of this. There are a bunch of other reasons as well. I'm very happy to go into deep technical deep technical discussion about that if you really want to. So what does this give us? The real key here is that we get fully enriched data. So we're bringing together all of those bits of work that the analyst would have to do manually. So we're getting much better data quality from that. We're getting the real context. We're getting what actually happened, not what the world looks like 2 hours later when you get around to it. we're also getting a real consistency to the way that we process this data. Another element of what we're doing with our platform is taking a lot of the benefits of the flexibility of the schema on read concept that we've been talking about for many, many years in Hadoop world, and applying that so that we can create low effort, consistent data models with nice, constant semantic meaning, which you can then apply analytics on and apply data science and apply all these kind of fancy machine learning pieces on. So bringing these together and bringing together the ability to do that gives us several things. Firstly, it gives us the ability to triage those events much faster, more intelligently, apply better analytics on top of them. It also, therefore, gets us much better coverage. If we can apply if we can make those decisions that poor analyst who was looking at his 100,000 events scrolling past his screen all day, if we can make him that little bit more efficient and take down that time that it takes for him to determine whether something's real or not real, then we can create huge efficiency, which enables us to get much better coverage of those data, of that data. We can get through a lot more of that 100,000 if we can make it more efficient. So you get much more efficiency out of your people. Or you can, you wouldn't necessarily need to say you need fewer security people. I'm not going to talk myself out of an industry. But it enables you to massively reduce your risk by enabling you to get much better coverage over your data. And that we really do by this concept of single view of risk. So that kind of happens with the triage stage as well. But we kind of get another benefit out of this as well. One of the other things that we get asked a lot is essentially, that's all very well. I mean, we're currently, we're doing tactical operational stuff. We're dealing with incidents. We're trying to get, we're just trying to stay afloat, is what a lot of security departments tell me. That's great. But once you've achieved that, you then are able to do a number of other things to provide much more intelligent views of your business's state of risk, for example. Because we're building everything on a big data platform that has the ability to store and process large amounts of data over time, we can then start to bubble all that together, take that fully enriched data, take a full picture of your organization's risk stance, and bubble that up into things like executive dashboards. So using things like the visualization technology that we can apply on top of Hadoop and on top of engines like Spark, for example, you can provide a much higher level view of your organization's risk stance, which allows you to make much more intelligent decisions about where to put your time, where to put your risk. It gets you beyond that kind of firefighting, everything is important state, to being able to genuinely understand where your organization, or what posture your organization has. And that's where we really bring in some of these other exotic data sources as well. So a lot of traditional security platforms will talk about network data, firewall data, proxy data. This is all good stuff, NetFlow data, raw PCAP data. That's all good stuff. But what we find is that there's also a lot of interesting security information in other more business-focused sources, which actually make it easier to understand a business risk posture as well. So things like physical security data, again, traditional security data, but also things like financial data, behavior data, HR-type data, bringing all of this into the security context and really creating that kind of genuine data lake approach can give you the ability to make much more intelligent decisions about your overall risk posture. So the other thing that we're able to do with the big data technologies and why it's important to scale is that we can actually store data for much longer. The longer term, we mentioned that kind of long-term attack pattern. With Hadoop, we can store queryable data for much longer. I typically hear people with retention policies of around about 90 days in traditional platforms. In Hadoop, because we have nice, cheap underlying storage, we can keep that much longer, we can query it much longer and start to see some of those 8, 9, 10-month long, 2-year long attacks as they progress. The other piece is that we focus very heavily on integration. We use a lot of Kafka in our platform. We have a number of people who've taken that to a kind of almost an extreme position where they've integrated that with full orchestration. So I have one customer who, for example, has a number of detection mechanisms that pick up ransomware. If they detect ransomware with a high certainty, then what they do is they integrate direct into their provisioning system and will completely rebuild a box. This is possibly an extreme version. I don't know about you, but if you're sat there working away and you're in your working day and then suddenly your PC decides to rebuild itself, you might not be very happy about it. So one of the other things they like to do is bring in some of their core business data so that they know that that box belongs to the CFO and that maybe it might be a career-limiting move to suddenly start an automatic rebuild right in the middle of his working day. So bringing all this kind of data together and providing that, that machine time, human out-of-a-loop detection can also be a very powerful piece, a mitigation piece, but it also does need that kind of intelligence that you get from the additional data sources to make the right decision. So how do we do it? There are a number of ways. We use a lot of network-level data. We create nice, consistent, open standards around that data so that we can apply multiple models, so that we can bring models from that we've produced, that customers have produced, that partners have produced, that the community has produced. We bring in a lot of business level data as well, so that we can really genuinely understand the business risk level approach to this data. We use the massively scalable platforms, which I'm not going to go into in detail here because they're pretty much sure everyone here is going to be talking about that to you. Traditionally, what people tended to do with this, though, was to take those platforms and kind of cobble it all together on their own. And you certainly can do that. You can take all the bits, all the tools that we have in our toolbox, and produce solutions which do this. What we've produced is essentially a reference architecture or implementation, a framework. You could squint at it and call it a fully realized solution, which provides essentially the best way of doing this. And what this is a result of many of our people, many of our experts sitting in meeting after meeting after meeting, drawing out essentially the same DIY architecture, the same kind of approaches, and finding that every bank, every insurance company, every manufacturer was pretty much spending their time building the same plumbing. What we've done here is to build the plumbing for you, build a series of frameworks which handle the ingestion of the data, handle that enrichment of that data to provide real business context, and handle some of the analytics, which I would strongly urge you to go and see Casey's talks about some of the depth of that analytics and how we do some of the behavior profiling on that. And then all of the indexing, all of the loading at speed, all of the scaling and performance issues. This is what we've already done. We've provided this for you. It's all developed in the community. There are a couple of community resources there. The Metron Apache website is a good starting point for more information about this. We also have, of course, all the code there. I apologize, that's actually, that's now changed. You notice there that it says Incubator Metron. Yeah, Metron was an Apache incubation project. When was it, April? In April, it officially became a top-level project. So it is now a full top-level Apache project with a nice, strong, growing community underneath it. And you can see from our commit frequency there that we have a heavily engaged community, both from Hortonworks and actually around the world. In fact, now we've got a number of international committers from a large number of organizations as well, which gets us to that top-level project status. So with that, I think we've probably hit time. So thank you very much. I hope that was interesting. And if you want a deep dive on some of those detection capabilities and some of the analytic capabilities, then do go to Casey's session on the behavior profiling, which is tomorrow, and on the model as a service, which is on Thursday. Those will be deep dive sessions. So for anyone who wants to see the raw tech of how we're doing all this and some actual live demos of the platform, then I strongly suggest those sessions as being your next port of call. And with that, thank you very much. And if there are any questions, I think we got some time for some questions. Yeah, I think there is a microphone.
What do you think the other team will do? And where is this all going?
So knowing what I know, what do I think the bad guys are going to do?
Right. Based on this evolution step of the good guys, what will be the response of the bad team? And where is this all going? Sort of just your projection.
So how do the bad guys stop us now we've got some collaboration and a community of our own?
Like, why couldn't they use machine learning?
Why couldn't they use machine learning? They do use machine learning. So, what we're saying, what we're saying here is that we're not getting rid of the arms race. What we're trying to do is slightly even the playing field. Right now that playing field is pretty skewed. I mean, that stat we had about the cost of a DDoS, $5 versus $40,000 on the defense side. That is just a massively skewed playing field right now. The key to solving that is actually collaboration and community, as well as just the pure tech of the machine learning models. Part of what we do with our platform is to provide more intelligent threat intel, for instance. So a lot of, right now, the good guys do collaborate. They share lists of bad guys. They share lists of known bad signatures. You get blacklist services which provide you information about known compromised servers, for example. What we're doing is taking that to the next level and providing that sharing at the model level, so the algorithmic level and a pattern of behavior level, rather than at the individual bad actor level. So we're providing the ability to detect bad guys by behavior, not by an individual instance. So how does a bad guy respond to that? Arguably, that could change some of the behavior. They have to start being much more erratic. They have to start actually thinking about things like preventing regular periodicity of their attacks. If you look at a lot of attacks involve a technique of beaconing, for example. So they will regularly at a given time go and talk to a command and control server to find instructions on how to spread an attack or what to do or whether to launch a DDoS. Those kind of things. At the moment, not many people actually detect, which is kind of silly because they're sort of easy-ish. But so the bad guys might have to start being much smarter about avoiding known pattern behaviors or avoiding repeatable pattern behaviors. So that's something that you could start doing. How am I going to hack things in 5 years' time when everyone's got this? I think some of the other interesting things are that the bad guys will have to evolve much faster to keep up with the algorithms. And because you're starting to be able to apply algorithms which can be retrained on data more regularly, the bad guys will have to evolve much faster. So to an extent, that is a little bit of an arms race piece. Kind of offensive machine learning is another kind of option on the bad side. Can they use machine learning algorithms to try and interpret or try and reverse engineer our machine learning algorithms, for example? There are some very interesting hacking attacks actually on machine learning algorithms, for example. So there have been a few papers about how people have used machine learning as a services and been able to reverse engineer the algorithm that they're using by feeding them certain data inputs. That's the kind of thing that you might start seeing. But again, that's the kind of behavior that then just essentially feeds back into the detection process. So there is an ongoing arms race. We're just giving ourselves slightly better weaponry on the protection side. I was going to say, I think of a number of other things, but it's an interesting question. Thank you. Do we have a, sorry, but microphone's closest. Okay.
Could you speak a little bit more about, with your last slide showing kind of the reference architecture, can you talk a little bit more about like what Metron is? Is it the glue code putting those things together? Is it new analytics that you're going to be giving to the community that helps detect these things? Like, what is it more specifically? As you showed all those contributions, what are a lot of those contributions actually is what I'd like to hear more about. What is the architecture? Like, what are you building?
Yeah, sure. So what Metron is as I said, a reference implementation of the framework to do a lot of these things. So what that provides is, we also provide some reference implementations of specific examples. So we provide a number of sensors focusing around network data, deep packet inspection, intrusion detection systems, NetFlow. We also provide a behavior profiler. What we don't provide at the moment is the realized use cases and the specific models and examples around that. But that's something which is very much coming at the moment. We do actually, no, we do provide a few of those now, kind of. Yeah, we've got a few example sets. We've got some repos out there which include example configurations for particular use cases, detecting particular kinds of behavior, particularly things like lateral movement. There are also, there are some early versions of community models in the machine learning pieces which go into Metron. We also provide actually a user interface for configuring, managing, running the rules side of that and the triage side of that, and in fact for investigation, and a number of default dashboards and some default reports as part of Metron as well. So there's quite a lot in there now. Yeah, it's growing very rapidly. So we and others are doing a lot of work on that. We also provide a number of standard parsers for common device formats and some of the common security formats like Ceph and syslog and the kind of usual sort of usual candidates. Bluecurts, Palo Alto's, ASA kind of parser support. So there's quite a bit in there now. And if you want to hear a little bit more about some of the details and how those work and see some of those actually in action, then as I say, one of our data scientists, Casey, will be talking a lot more about that in excruciating detail. But yeah, so there's quite a lot of real stuff in there. But I think we have one next, and then yeah.
Thank you. How production ready would you call Metron?
So how production ready is it? So it's based on a very solid platform. So we're pretty confident in the production readiness of the Hadoop piece and the NiFi piece that we use underneath it. So those have been around for a good long time. We've been doing a lot of work recently on making Metron more production ready. So some of the key work we've done around that is around the deployment of Metron. So it's now deployed as an Ambari MPAC. So the management configuration and installation is all through Ambari. So that's a nice kind of DevOps process to it. The other piece of that was a lot of work we've done around security hardening, so full Kerberos support, which is a key production readiness requirement for a lot of people. We've also been doing some benchmarking recently to verify the performance, and out of that we've got preliminary results on we haven't actually published these yet, but we've got some preliminary results around a 6-node cluster we were running, which was getting about 1 million events per second pushing through of network traffic. So we're pretty confident in the scale and performance side of the production readiness. So with all those pieces, there is still some assembly required. So it's not necessarily for the faint of heart, and it's not a thing that you just download and make run in 5 minutes as on your own. But we've got some good, strong production cases, and we've got some people who are taking it live in some really quite large environments with some really quite sensitive data.
Okay, so there are some corporate users running it already.
Yeah.
Okay, thank you.
Yeah, hi. We've been using the Metron, I think 0.2. It's very early.
There you go.
So it's, but the thing is that we had problems like trying to ingest the data. So we wrote a lot of NiFi, like a lot of custom code. So it was like the most painful part, like So I mean, now it is almost a year. So are you doing something like to make it easy to just drag and drop the servers or So we try to make like a config file where we just put in the server name and it just ingests itself. So something like that. There's a lot of work.
Yeah.
But are you doing anything in that area?
So you said Metron 0.2.
Yeah. Probably
Oh God, yeah. How many releases have we had since 0.2?
Probably 1 year or
2 major ones.
Yeah, 2 major version numbers out. So yeah, we've done a lot of work around that, particularly around a lot of the early versions focused very heavily on the engine and the underlying platform. A lot of the work that we've been doing recently is essentially dealing with exactly that pain. So provided some work around a management UI, which provides a visual approach to handling that ingest and building out parsers and building out the enrichment workflow, for example. So that's now in a guided UI form through the new Metron management UI. So that makes life a lot easier. for that kind of side of handling the ingest pieces. What else has changed since 0.2? Kind of everything. So there's a lot of work that we've been doing to simplify that process of handling ingest, and we certainly have people who've been bringing on new data sources at quite large. They bring on a lot of new data sources quite effectively and quite efficiently. There's also actually some work being done. We're not done yet, I should point out. There's some work being done in the community right now to make that even more plug and play for custom parsers and custom ingest sources, for example, to isolate that and make it a lot easier as well. So there is a lot of work that's been done, particularly around the kind of point and click or guided UI approach to doing that. And there's a lot of underlying platform work that's been done in 0.3 and 0.4.
So all this are Lombardi or is it like MiFi?
It's a Metron-specific management UI. So I think is that time. So if anybody does have any other questions, then please feel free to get in touch with us. Find me on Twitter at Cyreb, find me on LinkedIn, find me wandering around the building. And thank you very much.
I would like to get your contact.